Deep in the darkness of space, beyond familiar planets and stars, lies something that has long eluded our understanding. Observers exploring the far reaches of the solar system began noticing peculiar anomalies. The orbits of objects in the Kuiper belt, inexplicable by the gravity of known planets, hinted at something greater than mere chance. These inexplicable trajectories prompted scientists to ponder the possible existence of another planet, a ninth one, dark and mysterious. Mathematical models and computer simulations started painting a chillingly coherent picture, an unknown celestial body whose mass and orbit influence the movements of numerous objects beyond Neptune. But what if this unseen planet truly exists, governing hidden processes at the edge of our star system? With each new observation, the hypothesis of a ninth planet became increasingly compelling. Definitive proof of its existence has yet to be found, but doubts diminished with each discovery. Researchers continued their quest, driven by the desire to unravel one of the most captivating mysteries of modern astronomy. The first attempts to detect the mysterious ninth planet date back long before modern observations and calculations. Interest in the possible existence of another planet arose as early as the late 19th century, when astronomers began noticing deviations in the orbits of known planets, particularly Uranus and Neptune. These discrepancies led scientists to hypothesize the existence of another planet exerting gravitational influence on these giants. The first serious attempt to find the unknown planet was undertaken by the American astronomer Percival Lowell. In the early 20th century, he proposed the hypothesis of Planet X and even built a special observatory in Flagstaff, Arizona, dedicated to its search. Despite years of effort, Lowell was unable to find evidence of the new planet. Nevertheless, his work was not in vain. The data and methodologies developed by him and his team proved useful to other researchers later on. With the discovery of Pluto in 1930 by Clyde Tombaugh, many believed that Planet X had finally been found. However, it soon became clear that Pluto was too small to explain the observed gravitational anomalies. This prompted scientists to continue the search. From the mid-20th century to the beginning of the 21st century, astronomers turned their attention to numerous celestial bodies in the Kuiper belt and beyond, such as Eris, Sedna, and others. These objects also exhibited unusual orbits, reigniting interest in the hypothesis of a large, unknown planet. The challenge astronomers faced for decades was that the ninth planet, if it exists, likely resides at a vast distance from the Sun and has a highly elongated orbit. This means the planet could spend most of its time far beyond the visibility of even the most powerful telescopes. Moreover, its movement across the sky could be so slow that it would be extremely difficult to distinguish from many other objects. In 2016, interest in the possible planet surged again, due to the research of Michael Brown and Konstantin Batygin from the California Institute of Technology. They conducted a detailed analysis of the orbits of trans-Neptunian objects, TNOs, and found that several of these objects had similar anomalies that were difficult to explain by chance alone. Their findings suggested the possible presence of a large planetary body, roughly 5–10 times the mass of Earth, on a significantly distant orbit from the Sun. Brown and Batygin's work sparked a wave of interest and new observations. Scientists worldwide began using the most advanced tools and technologies to attempt to confirm the existence of the hypothesized ninth planet. However, researchers faced serious challenges. One of the main issues is the need for prolonged observations to confirm the hypothesis. If the planet is on an elongated orbit, its orbital period could range from 10,000 to 20,000 years, making the search particularly daunting. Another significant obstacle is the abundance of celestial objects with anomalous orbits unrelated to the ninth planet. Astronomers must carefully filter data to avoid false leads. Moreover, the nature of distant objects makes them very faint and difficult to distinguish even for powerful telescopes. International cooperation is also crucial. Observing the suspected planet requires significant resources and time, prompting scientists from different countries to collaborate. Joint projects and data exchange accelerate the research process and increase the chances of success. Each step in this direction brings us closer to unraveling one of the most exciting mysteries of the solar system. We can only wait for technology and scientists' efforts to lead to the long-awaited discovery that will reshape our understanding of the boundaries and structure of our celestial neighborhood. With the advancement of technologies and observation methods, the chances of detecting the ninth planet of the solar system have significantly increased. Modern tools and approaches enable scientists to overcome numerous obstacles faced by their predecessors. One of the key instruments used in the search for the ninth planet is the Subaru telescope, located atop Mauna Kea in Hawaii. Equipped with the state-of-the-art Hyper Supreme Cam, this telescope boasts high sensitivity and a wide field of view, making it ideal for detecting faint objects in the distant regions of the solar system. The Hyper Supreme Cam allows astronomers to conduct detailed surveys of the sky and identify small, dim objects that were previously inaccessible for observation. Another important tool is the James Webb Space Telescope, JWST, scheduled for launch in the coming years. Operating in the infrared spectrum, JWST will be able to see cold and distant objects that emit little visible light. This capability is crucial for detecting the ninth planet, which is likely too cold and dim to be noticeable in the visible range. JWST's infrared sensitivity will enable astronomers to more effectively search for potential candidates for the ninth planet. Modern data analysis methods also play a crucial role in the search for the ninth planet. Computer simulations and models allow scientists to predict what the orbit of the unknown planet might look like and how its gravitational influence manifests in the movements of other objects in the solar system. Such models help narrow down search areas and focus observations on the most promising parts of the sky. Powerful supercomputers process vast amounts of data collected by telescopes and identify weak signals that could indicate the presence of the ninth planet. Modern technologies allow scientists to conduct joint observations using multiple telescopes simultaneously. This coordination helps increase the accuracy and reliability of observations, as well as cover more extensive areas of the sky. For example, telescopes located in different parts of the globe can simultaneously observe the same objects, providing more data and enhancing the likelihood of detecting the ninth planet. One of the key methods used in modern searches is the method of hidden scanning. Instead of directly searching for the planet itself, scientists look for its gravitational influence on surrounding objects. This is particularly important for objects far beyond Neptune's orbit, where direct visual identification of the planet may be difficult due to its low brightness. By observing the orbits of trans-Neptunian objects and identifying patterns in their movements, scientists can infer the existence and parameters of the hypothetical ninth planet. Technologies also include the use of robotic telescopes and automated observation systems. These systems can continuously monitor specific areas of the sky, collecting data with high frequency and precision. Robotic telescopes can quickly respond to changes and redirect their observations to new, interesting objects, significantly enhancing the efficiency of search programs. An important aspect of modern methods is also the use of data obtained from different sources and combining these data into a unified database. For example, data from telescopes operating in different spectra, optical, infrared, radio, can complement each other and provide a more complete picture of potential candidates for the ninth planet. Data integration allows scientists to more accurately determine the position and characteristics of objects, as well as identify new potential targets for observations. Modern data processing methods, such as machine learning and artificial intelligence, also find their application in the search for the ninth planet. These technologies automate the process of analyzing vast amounts of data, uncover hidden patterns and anomalies that could indicate the presence of an unknown planet. Machine learning accelerates the search process and makes it more precise, which is particularly important when dealing with huge volumes of data collected by modern telescopes. Using numerical models, astronomers attempt to predict the exact whereabouts of this mysterious object and how it influences other bodies in the solar system. These models are constructed based on observational data and physical laws, enabling scientists to create simulations that reflect the possible position and behavior of the ninth planet. One of the earliest and most significant models that renewed interest in the ninth planet was the work of Michael Brown and Konstantin Batygin. Their model, based on observations of the orbits of trans-Neptunian objects, TNOs, showed that anomalies in the motion of these objects could be explained by the presence of a large planet. These anomalies include unusually elongated and inclined orbits that are difficult to explain without additional gravitational influence. Brown and Battigin's models predicted that the ninth planet could reside on a highly elongated orbit with a large eccentricity, and its mass is estimated to be approximately 10 times that of Earth. These parameters allow the planet to affect the orbits of TNOs even while being significantly distant from the Sun. But how do you accurately model the orbit of an object that hasn't been directly observed yet? These models involve numerous variables and require tremendous computational power to conduct simulations. Scientists utilize supercomputers to calculate orbital parameters and predict the possible location of the ninth planet. These simulations help narrow down the search area and determine where telescopes should concentrate their observations. One method used in modeling involves backward analysis of TNO orbital parameters. Scientists take known orbits of these objects and, using numerical integration methods, attempt to calculate the gravitational influence needed from the unknown body to explain the observed anomalies. This approach helps create more accurate models and identify key areas for further observations. An intriguing aspect of orbit modeling is that it can also provide insights into possible characteristics of the ninth planet, such as its mass, composition, and even structure, all of which can influence gravitational interactions with other objects. Researchers use this data to hypothesize what this mysterious object might be like and how it could have formed. But what if the ninth planet does exist and its orbit is so unique that current models cannot precisely predict it? This question drives scientists to continually refine their models and seek new data that can either confirm or refute the hypothesis. Current numerical models also consider the influence of other factors, such as interactions with other large planets and the interstellar environment. These models are becoming increasingly complex and accurate, enhancing the likelihood of successfully detecting the ninth planet. Numerous simulations and data analyses are creating a more detailed picture of the potential location and movement of this enigmatic object. An important aspect of modeling is the continuous updating of data and improving models as new information becomes available. New observations, discoveries of new TNOs, and improved telescopes help scientists refine their models and make them more accurate. Modern numerical models are dynamic tools that constantly adapt to new data and discoveries. As technology and observation methods continue to advance, the chances of successfully detecting the ninth planet continue to grow. The question remains, when and where will this long-awaited discovery be made? Modern telescopes such as Subaru and the James Webb Space Telescope provide extensive data sets that require careful analysis to detect faint signals indicating the presence of a hypothetical planet. Data collected by telescopes undergoes a multi-stage processing. Initially, automated systems filter the information, identifying potentially interesting objects. These data then undergo detailed analysis using complex algorithms and machine learning methods capable of detecting hidden patterns and anomalies in the motion of trans-Neptunian objects, TNOs. These anomalies may indicate the gravitational influence of a ninth planet. If detected anomalies match predictions from numerical models, it increases the likelihood of finding the sought-after planet in the specified area. Scientists use data on the position, velocity, and direction of TNOs to refine their models and narrow down the search area. Space missions like New Horizons also contribute to data analysis. This mission, which flew past Pluto, continues to gather information about the outer regions of the solar system, including the Kuiper Belt. Data from such missions help scientists better understand the structure and dynamics of distant regions, aiding in the search for planets. Data collected by various observatories worldwide are pooled and jointly analyzed, providing a more comprehensive and accurate picture. With each new dataset, the search area narrows, bringing us closer to the long-awaited discovery. In recent years, astronomers have made several important discoveries that support the hypothesis of a ninth planet's existence. One key discovery has been the identification of new trans-Neptunian objects, TNOs, with unusual orbits. These objects, located beyond Neptune, exhibit anomalous trajectories, that are difficult to explain without the presence of a large gravitational perturbing body. One such object is 2015 TG 387, also known as the Goblin. Discovered using the Subaru telescope, it drew attention due to its extremely elongated orbit, which researchers believe could be a result of the gravitational influence of a ninth planet. Such discoveries strengthen the hypothesis that a massive object in a distant orbit affects the movements of TNOs. Another significant discovery was made in 2020, when two new TNOs with orbits similar to those predicted by models of the ninth planet were found. These objects showed similarities in the inclinations and eccentricities of their orbits, further indicating the possible presence of a large gravitational perturbing body in the outer reaches of the solar system. A notable addition to these findings has been data obtained from the Transiting Exoplanets Survey satellite, TESS. While TESS is primarily designed to search for exoplanets, its sensitive instruments can also be used to observe the motion of objects within our solar system. Recent observations with TESS have identified additional anomalies in the motion of TNOs, further intensifying suspicions regarding the existence of a ninth planet. Numerical models and simulations conducted on supercomputers continue to support the hypothesis of a ninth planet. They show that such an object could explain not only the orbital anomalies of TNOs, but also other mysterious phenomena, such as the tilt of the Sun's rotation axis relative to the ecliptic plane. However, despite all these discoveries, definitive proof of the ninth planet's existence remains elusive. Astronomers continue to study data and conduct new observations in hopes of finding conclusive evidence. The discovery of the ninth planet could fundamentally change our understanding of solar system formation and significantly revise existing theories. One of the key puzzles that this hypothetical planet may help resolve is the process of giant planet formation and migration. According to current models, giant planets like Jupiter and Saturn formed closer to the Sun and then migrated to their current orbits. However, the detection of the ninth planet, with its presumed highly elongated orbit, could indicate more complex and multi-stage migration processes. This suggests that our solar system experienced more intense dynamical interactions during its early stages of development than previously thought. The ninth planet could also help explain the distribution and properties of trans-Neptunian objects, TNOs. Their anomalous orbits could result from gravitational interactions with a large object situated on a distant orbit. This discovery could confirm that the planet formation process was much more chaotic and less stable than previously assumed. If such a large object could form and exist in our system, similar processes might be occurring in other planetary systems as well. This would alter our understanding of the prevalence and diversity of planetary systems in the universe. Finally, the discovery of the ninth planet could also impact theories on the origins of comets and other small bodies in the solar system. If the planet exists, its gravitational influence could have contributed to the migration of comets from the Kuiper Belt to the inner regions of the system, explaining some observed features in comet behavior. Finding this planet may compel us to reconsider many aspects of planet formation theory, not only within the context of our solar system, but also on a broader astronomical scale. Considering all the recent advancements and accumulated data, astronomers look optimistically towards the future, making predictions regarding the time and place of possible detection in this decade. Based on numerical models and observations, researchers speculate that detection could occur within the next few years. One of the primary tools that could play a crucial role in the search is the James Webb Space Telescope, JWST. Due to its high sensitivity in the infrared range, JWST is capable of detecting faint, cold objects at significant distances from the Sun. It is expected to actively participate in the search for the ninth planet once its current missions are completed and its instruments are calibrated. Additionally, future discoveries may be supported by ground-based telescopes such as Subaru and the recently built Vera C. Rubin Observatory. The latter, with its wide field of view and high sensitivity, will regularly scan the sky, significantly increasing the chances of detecting the hypothetical planet. Since its launch in 2024, the observatory has already demonstrated potential in detecting faint objects at the edge of the solar system. Based on current data and models, Astronomers speculate that this planet could be located at a distance of 300 to 1,000 astronomical units, AU, from the Sun. The highest probability of its detection is concentrated in an area roughly opposite Orion in the sky, based on the analysis of trans-Neptunian object orbits and gravitational interactions. Regarding timing, many scientists are hopeful for significant progress within the next 5 years. This optimism is based on improved instruments, more accurate models, and a large volume of new data expected from the launch of new telescopes and observatories. The time and resources invested in this search also play a crucial role, and astronomers are confident that their efforts will soon lead to the long-awaited discovery. Despite all the challenges and uncertainties, predictions regarding the timing and location of the 9th planet's discovery are highly optimistic. Thanks to modern technologies and methods, astronomers continue to approach unraveling one of the most intriguing mysteries of our solar system. The search for the 9th planet is one of the most thrilling and intriguing pursuits in modern astronomy. Regardless of whether the 9th planet is discovered in the coming years, the research itself has already significantly impacted our understanding of the solar system and the processes occurring in its distant regions. Discoveries of new trans-Neptunian objects with anomalous orbits, advancements in numerical modeling techniques, and the application of modern telescopes have all greatly advanced our knowledge and pushed forward new theoretical developments. These studies not only aid in the search for the 9th planet, but also contribute to a deeper understanding of the dynamics and evolution of our solar system as a whole. The potential discovery of such a planet extends far beyond our own system. It could influence theories of planetary system formation in other stellar systems, enhance our understanding of planetary migration and interactions in young star systems. It may also broaden our horizons on how planetary systems form and evolve across the universe. Future steps in research will involve more detailed observations, improved modeling, and analysis of new data. Modern and upcoming telescopes like JWST and the Vera C. Rubin Observatory will play crucial roles in these investigations, providing scientists with tools for precise data analysis and discovery. International cooperation and information exchange will remain critical for successfully unraveling this mystery. The search continues to be one of the most captivating and promising avenues in astronomy, opening new horizons and prompting further exploration and discovery of uncharted areas within our solar system. Stay tuned for updates to stay informed about the latest advancements and discoveries in this exciting field. Subscribe to our channel to not miss out on important updates and to learn more about the mysterious and awe-inspiring world of astronomy.